webinar. Thank you also, Diedert, for your introduction. My name is Julian van Tilburg, and I'm a consultant at Ecofis. And the work I present today is based on analysis and a report we executed together with the European Copper Institute, focusing on energy efficiency obligation schemes, and for this topic specifically on measurement and verification within those schemes. Now the topic of measurement and verification schemes we expect will be very relevant in the next years. Currently, the Energy Efficiency Directive is undergoing a revision and is currently in trilogue discussions. And the expected implementation of this revised Energy Efficiency Directive will be probably later this year. Now, the biggest change of this revision will be an increase of the energy efficiency targets for the period after 2020 to 30% energy savings in 2030 ultimately. Now these increased energy efficiency targets will give rise to additional implementations of measurements, and we also expect to see a lot of measures in the next years that are new, that have not been implemented a lot in the past years, and we expect to see innovation around those measures as well. Now, this links to measurements and verification methods, because we expect that new innovative measures will also have specific demands on the way these are measured and verified. And also part of these measures directly involve human behavior, basically the consumption of energy and the human behavior affecting the consumption of energy. Now, the way you measure and verify your energy efficiency measure should also take into account the way people use energy. And that will be the topic of today's webinar. Looking at Annex 5 of the Energy Efficiency Directive, there are 4 types of measurement and verification methods prescribed in the EED. These are the deemed savings approach, the meter savings approach, the scaled savings approach, and the surveyed savings approach. Now, basically, the deemed savings approach uses a predetermined savings parameters to calculate the impact of a energy efficiency measure that is installed. So these deemed savings rely heavily on reproducibility of energy efficiency measures, but also on a large statistical number of, for instance, buildings where these measures are being installed, ensuring that the impact of an energy efficiency measure is sort of similar across all those buildings. Now, when we look at metered savings, these are the savings that result from a direct metering of actual reduction in energy use. These metered savings are used a lot in industrial energy efficiency measures, or also in large commercial buildings, but they require more attention from the regulator. They require audits and analysis, and are therefore not favored so much when it comes to energy efficiency measures in residential buildings, for example. Now then we also have the scaled savings based on engineering estimates, and these kind of MFV methodologies are typically used when it's difficult to measure data in specific installations, but when based on an engineering analysis, it is possible to have an estimate of what savings will be under certain circumstances. Now, and finally, there's also the methodology of surveyed savings, where basically surveys and also audits are performed asking consumers how they use their energy. And this is typically a MNV approach that is being used when it comes to energy efficiency behavior measures. Now, in our analysis, we focused specifically on MNV approaches for standardized energy efficiency measures. There is in the member states that have implemented energy efficiency obligation schemes, there is a difference between the standard energy efficiency measures and the non-standard energy efficiency measures. Now, typically for the standard measures, we see that deemed savings methodology is typically used, where based on a couple of few parameters, the energy efficiency savings are calculated for specified sets of energy efficiency measures. So especially in standardized measures, specifically in residential buildings, the deemed savings are being used. Also in commercial buildings, we see the deemed savings being used, but we also see the scaled savings, basically taking into account specifics of commercial buildings, also the surface area of floors in commercial buildings. And these two, the deemed savings and the scaled savings, are predominantly used for these sectors. Now, to give you a flavor of what deemed savings could look like when implemented for standard measures in the built environment, this is a screenshot of the tool that is being utilized in the energy efficiency obligation scheme in the United Kingdom. And through a series of choices, depending on the specific situation of your building, you are basically led to a predefined savings value. So if you install, for instance, a boiler in a house, you'll get different deemed savings than installing that same boiler for a bungalow building. Now, these deemed savings work relatively well when it comes to residential buildings, but in pushing the limits further on the energy efficiency in buildings, we see that in some cases we reach limits of where deemed savings are still accurate. To give you an example, here's a graph displaying the actual and the theoretical gas consumption in the Netherlands. What you see on the x-axis are the energy efficiency labels or energy performance labels, A being the best performing buildings and G being the worst performing buildings. And what you see is that there is a large deviation because between what is actually consumed in terms of gas in these buildings compared to what is theoretically expected that the consumption will be. Now what you see is that for the poorly performing buildings, the actual consumption is much less than what is theoretically expected based on also on engineering estimates. And this is because when buildings are not well insulated, for instance, the energy bills can become quite high, and people change their behavior to save energy for heating. Now, when the building performance improves because of insulation, then part of the improvement will be used to improve the comfort levels in the buildings. For instance, people will, instead of heating only a single room, they will start heating all rooms because it's so cheap. They need so little energy compared to the previously. Now, this is commonly termed a rebound effect, and happens for almost all energy efficiency improvements that are being applied. Human behavior adapts to the new situation and partially reduces the expected energy efficiency gains. Now, this is a situation where deemed savings reach the limit of what is still acceptable in terms of accuracy. It does matter whether your, for instance, boiler will be replaced in a bad performing building versus a good performing building. And these factors need to be taken into account when calculating your energy savings. Now, there are also other examples where we see a potential breakdown of the deemed savings methodology in the future. Another example I want to mention is labeled here as the person-machine interaction. Over the next years, we expect an increased implementation of smart building measures like building automation and control systems or energy management systems that will control part of the energy systems in buildings. Now, this is all automated, but it will impact also the comfort levels in buildings, and people will adapt their behavior to the building automation and control systems. Now, of course, in implementing these measures and claiming the savings due to these measures, you want to be sure that people living in these buildings also optimize the settings for these building automation and control systems to make sure that they indeed reach the savings that are expected from these measures. And this also applies for energy management systems. The interaction between a person and the energy systems in a building will become more and more relevant in the future. A third example of where we expect to reach limits in the application of deemed savings is when it comes to outlier buildings. The strength of deemed savings is in having large numbers of comparable buildings and being able to sort of statistically average out the small variations that you expect in a group of comparable buildings. But when buildings are really different compared to the reference group, then deemed savings methodology does no longer apply, and you need to think about different ways of estimating the energy savings in such a situation. Now, of course, it is possible to visit these buildings to determine the energy savings from audits or maybe from metering. But you want to be sure that the costs are associated with estimating these savings or measuring these savings are appropriate compared to the savings that you actually achieve in terms of energy use. And that's the fourth point. It is possible to measure the impact of energy efficiency measures in buildings, but you want to make sure that the transaction costs for doing these measurements is as low as possible, both for the regulator, for the obliged party, but also for the energy user in the end. Deemed savings are effective because they have rather low transaction costs, but you want to make sure that also with the increasing energy efficiency targets in Europe, with new and innovative energy efficiency measures, that you can keep these transaction costs as low as you want them to be. Now this is one of the reasons why we looked into advanced measurement and verification methods. This is a topic that is being actively discussed in scientific or academia environment. It's a very hot topic in the United States, but also in Europe. Some knowledge institutes are investigating this, and the four drivers I just mentioned in why deemed savings may no longer be applicable in all situations in the future is basically complemented with another driver, and that's the implementation of smart meters across Europe, or actually across the world, as you can see in this figure, but also in Europe. We expect over the next decade to be to see a large penetration of smart meters in buildings, residential buildings and commercial buildings. Now, these smart meters can prove to be a very nice way to do remote monitoring of energy savings with a accuracy that can be better than we see for deemed savings. Now, and that's the key feature of advanced MMV, as this is commonly phrased. By using smart meter data with hourly or even sub-hourly resolution, you are able to collect data from energy use in a much more granular way as you're able to collect it by basically looking at annual energy use. Smart meters integrate well with energy management systems in the buildings, but also after collecting this data, it is possible to do remote analytics on the data to be able to calculate patterns in energy use, and possibly to estimate the energy savings that result from measures that have been taken in a building. Now, one additional advantage is that having these very fast collection of data and analytics processes, it's also possible to feedback this information to the building, to the smart system in a building, but also to the energy user. And also this near feedback, near real-time feedback of information is in itself a energy efficiency measure, or could in itself be an energy efficiency measure. Now, to give you some examples of current investigations into advanced measurements and verification, I show you some images from the Fraunhofer Institute, where people are investigating whether they can use smart meter data to identify the energy performance of specific elements inside a building. So on the left figure you see a process line in an industrial environment with specific machines that require energy. Now, the energy use of a machine is often uniquely linked to that machine, and by analyzing the energy patterns, it can be possible to identify what machine is using how much energy at what moment in time, as is depicted in the figure on the right for a domestic application. You see in the top graph, you see the data that is collected through the smart meter with a very high time resolution. Now, by analyzing all these peaks, it is in some cases possible to really identify the individual appliances that are causing these patterns. So, for instance, here you can see the impact of a dryer, a water heater, dishwasher, etc. So this method of identifying individual appliances in the smart meter data is a way to also measure the energy efficiency of buildings. This information can be linked also to the use of gas in buildings. And by doing the proper number crunching, it is possible to identify the impact of, for instance, insulation in a building, or a better parameter setting for boilers or for heat pumps. Additional advantages of advanced MMV are that it's possible to analyze this data remotely, so it's no longer required to visit these locations as often as was necessary for audits, but the data can be processed offline, and it could be possible to have fewer audits or fewer inspections, as the data is already giving you a good indication of what are the energy savings that are being achieved. And now using this kind of data also gives you additional advantages that are not strictly limited to energy efficiency, but it would also be possible to have demand response functionalities, interaction with human behavior, to limit electricity demand in terms of shortages, or when the electricity grid is congested. Another example that I would like to show you is an example from North America. A Canadian power company and two American research institutes investigated whether the smart meter data can also be used in residential buildings to identify energy savings, but also to be able to have a way of updating the deemed savings parameters in a faster way as is commonly done. And I will show you some of the results they obtained in this project. So basically what they did is they measured a typical energy use pattern over an entire year, including seasonal influences. And they used this energy use pattern as the baseline for their analysis. Then after applying a energy efficiency measure, they measured again their energy use, and they were able to determine a difference in the energy uses compared to the baseline that they expected to have. Now, they did not just map the meter data on the baseline they measured a year earlier, but they corrected the baseline also for seasonal influences and for other influences that impact energy use. So this gives you a really a projected baseline that is corrected for differences over the years. Now, by comparing this baseline with the meter data, they were able to determine energy savings. And typically, energy savings in the range of 5 to 10% of the baseline usage are large enough to be measured in such a way at a reasonable error level. And that's shown in this graph. Out of about 100 buildings, the errors were listed, the errors that came from using the advanced MMV compared to what was actually used in the buildings or saved in the buildings. And one can see that they were able to reach a median error level of about 5%, which is quite low, especially if you compare that to the error levels that you see when you use deemed scores for buildings that do not compare very well to the statistical average. And typically for these order of magnitudes of errors, it becomes interesting to use advanced MMV as an alternative for audits and inspections. But as they show, it also becomes an alternative for deemed scores. Basically by aggregating the measurements over a large set of buildings, around 40 already works, the total error can be reduced to about 1 to 4%. So basically by measuring continuously the energy performance of these 40 buildings, you are able to determine a sort of flexible deemed value that you can also use in comparable buildings, really limiting the transaction costs that would otherwise be required when doing a market consultation and engineering exercise to update the deemed savings. Now, to conclude, I mentioned several opportunities that may be brought by this advanced MNV method, especially when it comes to energy efficiency measures that impact human behavior, and when it comes to energy efficiency measures that are being implemented in buildings that are not very much comparable to the average buildings. Now, advanced MFV has the promise of being able to reduce the transaction costs for MFV that would otherwise be required in such situations. The use of MFV can result in more adaptable and more comparable deemed savings, but also in opportunities to steer the consumer behavior towards more energy efficient use of energy. Now, I mentioned that several knowledge institutes are already performing pilots on this in this topic, and we think that additional pilots are actually required to prove the applicability of advanced MFV, and these pilots should specifically show where the reproducible benefits lie, what kind of buildings are most suited for this approach, and also what would be the ideal setting for advanced MNV in terms of lowering the transaction costs. Another topic that is very important in terms of piloting and further policy development is the sensitivity of smart meter data. The example I showed on the disaggregation of energy use, this information is very sensitive to privacy and security issues, as it can in principle allow people to identify what people are doing inside buildings, and this information should of course be carefully protected. A lot of this information is already collected by commercial parties that, for instance, offer energy services or operate energy management systems. And this information is not easily shared by these commercial data owners. So also that would be something to investigate further, to find ways of accessing this data through additional channels or by having agreements with these commercial data owners. Now this brings me to a couple of next steps that we see at Ecofys that would be required to prove the advantages of advanced MFV in energy efficiency measures in buildings. As I mentioned earlier, the advanced MFV is mostly applicable when energy savings exceed 5 to 10% compared to the baseline. So if energy efficiency obligation member states would incentivize measures with large savings compared to the baseline, that would provide clear application potential for advanced MFV. And we can imagine that this will also lead to an increased demand in energy efficiency measures that have high savings, and also products and services around those measures that ultimately result in low transaction costs for the regulator, but also low transaction costs for the obliged actors. Now, and as I mentioned before, the testing of these techniques in real-life pilot situations is crucial to determine the optimal sector applications, the feasibility for different kinds of energy savings, and to test and validate the data analytic software that is currently available. Now, and we think that over the years, as the smart meter penetration will increase in Europe, advanced MFE will become more and more relevant, and more situations will emerge where advanced MFE will be an integral part of the energy efficiency savings evaluation. This brings me to the conclusion of the webinar. Didit, I think now the floor is open for questions and responses to this story.